Nice to see you again. In this video, we'll do Chapter 7, and that's on hypothesis tests and confidence intervals in the multiple regression model, the model we worked out in the last chapter. And so we want to look at how to quantify the sampling uncertainty, that is the standard errors and those sorts of things. And as I just said, do a hypothesis test and confidence intervals. And remember, the model we have is yi is beta 0 plus beta 1 x1i plus beta 2 x2i plus all the way out to beta k xki plus ui. So we have some model in mind that looks like that. And there's two types of hypotheses we can think about in a model like this. One is about individual coefficients on the x's, and so looking at them one at a time. For instance, the null that beta 2 equals 0 versus an alternative that beta 2 is not equal to 0 or equal to 1 or equal to whatever. Just the kind of hypothesis test we've already looked at, and that's what we're going to start with. But you can also do hypothesis tests about multiple coefficients, like beta 1 equals beta 2, or beta 2 plus beta 3 equals 1, and that sort of thing. And we'll look at those types of hypotheses very soon in this chapter. So first we're going to do hypothesis test and confidence intervals for a single coefficient, a single beta. The betas are the coefficients. And really there's nothing new here. When you do OLS, that'll give you an estimate of all the beta hats, say beta hat j. And it will also give you sigma hat, beta hat j. That is the same as the standard error of beta hat j. And we didn't write down the formulas for these because they're very complicated, the multiple regression framework. But the computer program that you use, like we're using eViews, whatever one you use, would spit out these numbers after you do the regression. And so the first thing, we already know that the beta hats are consistent. Let me just note that sigma hat squared beta hat j, the estimate of the variance of beta hat j, of the estimator, converges in probability to the true value, that is, as n goes to infinity. That's what that converges in probability means. And so this is a consistent estimator. OLS is a consistent estimator of the standard error and of the variance. And so that's nice because in large samples we know we have both consistent betas and consistent standard errors. That'll give us consistent test statistics. Okay, so let's look at hypothesis tests to begin with, and then we'll do confidence intervals. And we can run through this fairly fast because there's really nothing new here compared to what we already did in chapter, what was it, in the earlier chapter on hypothesis testing. Is that chapter 5? I think so. So you do the regression, you do a regression, and you'll get beta naught hat, beta 1 hat, up to beta k hat, and their standard errors. You use that. Suppose that we're just going to do the null is that, say, beta j. Remember that weird notation they used, beta j0, some specific value. Suppose we just want to test that it's 0, or test that it's 1, or test that it's not. So this just says, this is just some number. This little 0 here just means it's a specific number, like beta j equals 5, or whatever it is we're testing. 0 is the most common. H1 would be beta j does not equal beta j 0, which in this case is 0. And so we're going to do that kind of a test. Then the t is just what it used to be. It's the estimated value of beta j minus the hypothesized value. In our case, this is 0 over the standard error of beta hat j. So this is just your hypothesized value that you set yourself, and this is what the computer package gives you, and that gives you your standard t statistic. For large n, and we've said greater than 100 for sure, or not for sure, but is pretty safe, you can do a one-tailed or a two-tailed test. And if, for the two-tailed, if the absolute value of t is greater than 1.96, you'd reject. And that's at a 5% level of significance. For a one-tailed test, this value is 1.64. But for a two-tailed test, it's going to be 1.96. It's just so the test is exactly the same as we did before, and the confidence intervals are also just what we did in the previous chapter, in chapter 5. The confidence intervals are identical. The formula, it is beta hat j. This would be a 95%. Beta hat j plus or minus 1.96 times the standard error of beta hat j, what I've been calling sigma hat beta hat j. And so that's just the same old confidence interval we had before. If you wanted a 90% confidence interval, then it's just beta hat j plus or minus 1.64 times the standard error, beta hat j. So no problem there. Exactly what we did before. There's not much to say. Let's do the test score example. And just do an example of this really quickly. Not sure we need it, but we may as well. So let's estimate a multiple regression model. Score hat, this is I think one we've seen before, 686.0, yeah it is, minus 1.10 times the student-teacher ratio, minus 0.650 times the percent English learners. So that's our estimated model. And then we have standard errors, 8.7. This was 0.43. And this one was 0.031. This is beta naught. This is beta 1. And this is beta 2 hat. So we've been interested in this class size variable. So let's have a null that beta 1 is equal to 0, and the alternative is beta 1 is not equal to 0. So to test that, we just find the t statistic and then compare it to the critical value, 1.96. So what's the t statistic? T will be equal to estimated minus 1.10 minus hypothesized 0 over the standard error of the estimate, 0.43, and that turns out to be minus 2.54. And since the absolute value of minus 2.54 is greater than 1.96, the critical value, we reject the null. We'd reject that beta 1 is 0. So even though this used to be minus 2.28 when we didn't have this variable in it, and we said that's an omitted variable bias. We added this in, and suddenly this became much smaller. But even though it's smaller, it's still statistically significant. So it still has significance in explaining scores. So that's a t-test. And we could have done one for here as well. That's going to be significant because it's basically this divided by this is what you end up with. And surely that's greater than 2. We won't do that one. If you were to look up the p-value for this, so you go to the back of the book in the table. This particular example is on page 220, by the way. You go to the back of the book and you look up the probability value for this, and you find that it was equal to, what is it, 1.1%. Remember, what that means is that if I go out here and find 2.54 and minus 2.54, the area in these two tails is equal to 1.1%. Since that's less than 5%, since the critical values are in here, 1.96, and here's the other critical value, 1.96, we're out there in the rejection range. This is the rejection range here. From there over and there over, we would reject the null because this is less than 5%. If this had been 8%, so we're inside these bounds, then we would fail to reject. So you can either do it by looking up the p-value, comparing it to 5%, but it's probably easier to just find the t-statistic, and you know the critical value is 1.96, and just move on from there. The confidence interval here, what's that going to be? What's the 95% confidence interval for this estimate? Well, it's going to be minus 1.10 plus or minus the standard error, 0.43, times 1.96. Usually I write those the other way around. No biggie. So that's minus, the range there is minus 3.90 to minus 0.52. So 95% of the time, that range will contain the true population value of beta 1. And since it doesn't contain 0, that's another way to do the test. You'd reject that beta 1 was equal to 0 at a 5% level of significance. All right. Now, let's continue with this example. Next thing that happens is the supervisor that you've been working for, the administrator, the superintendent, I think I said supervisor, asks, says, I can't get any more money for my budget. What is the effect of class size on test scores holding expenditures per student constant? So we want to control for expenditures per student and then see what the effect of class size is. And so let's add a variable to the model that controls for expenditures per student. And in fact, that's the variable, expenditures per student. And so we estimate this model with another variable in it, score hat equals 649.6 minus 0.29 times the student-teacher ratio plus 3.87 times expenditures per student minus 0.656 times percent English learners. Make sure you can see that whole thing there. I think you can. And then it's not exactly parallel. Oh well. And then the standard errors are 15.5, 0.48, 1.59, and 0.036. Is that a 6? 32. So now what's happened is we've added another variable to the model, expenditures per student. That's probably highly correlated with class size. Smaller class size mean a larger expenditure per student because of the extra teachers, for instance. You also have extra classrooms, so all sorts of other costs. And so we probably had an omitted variable bias because this is correlated and it probably has an effect on test scores. And adding this variable really reduces the effect of the student-teacher ratio. In fact, the T now for STO, so if this is beta 1 here, for the null that beta 1 is 0 and the alternative that beta 1 is not 0, the T is now minus 0.29 minus 0 over 0.48, which is minus, what is that? I got it written down here somewhere, minus 0.60. Since the absolute value of that is less than 1.96, we're going to fail to reject. So now it looks like the student-teacher ratio has no effect at all on the scores. And is that correct? The book has a story of a taxpayer now saying, why are we worried about spending so much to reduce class sizes when this has no impact on score or not? And the answer to that is, in this regression, we really can't say for sure that this has no effect because it's highly multicollinear. The correlation between STR and expenditures per student, what's that equal to? I wrote it down here somewhere. Sorry. It's minus 0.62. That's a pretty high degree of correlation between those variables. So what's happening is that it's hard for the program to tell whether it's this variable or this variable that's important. And so it may be that STR is still important, but it's getting picked up through this expenditure variable. And so you can't really tell for sure if this belongs in the model or not, or whether STR has an effect on scores. And so the answer to this is that what you need to do is a joint hypothesis. This is beta 0 here, beta 0 hat, beta 1 hat. This is beta 2 hat and beta 3 hat here, those variables. So the solution to figure out if these things are significant, we need to do a joint hypothesis because individually they may not be significant. This one actually turns out to be significant because 2 times this is less than 1. If I take 3.87 minus 0 over 1.59, that's greater than 1.96. So we would reject that that's 0. But sometimes what will happen with multicollinearity is both of these will be 0. You'll fail to reject that both of those are 0. That doesn't mean, though, that they're not important. What we have to do is a joint test because the multicollinearity messes up the t-test. So we're going to start looking at joint hypotheses. In this particular case, what we want to test is the null that beta 1 equals beta 2 equals 0 versus the alternative that at least one of the two is non-zero. So we reject this. This is a joint hypothesis. We're testing jointly that both of these coefficients are simultaneously 0. Note, this imposes two restrictions. We'll see why this is important in a few minutes on the model. Just writing the model in general terms. The model is y0, yi is beta 0 plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i plus ui. Okay. This is called the unrestricted model. Now our null is that beta 1 equals beta 2 equals 0. The alternative, I just had it here, I'm just reminding you, was that at least one is non-zero. This is called the unrestricted model, the UR. We can also look at the restricted model, and to get the restricted model, you impose the null. You impose these restrictions. So the restricted model is yi is beta 0 plus beta 1 is 0, beta 2 is 0, plus beta 3 x3i plus ui. So there's two restrictions. One is that beta 1 equals 0, and the other is that beta 2 equals 0. And you can write both the restricted and the unrestricted models, and we'll come back and use these later on for some tests. More generally, in general, we can write our model is yi is beta 0 plus beta 1 x1i plus beta 2 x2i all the way out to beta k xki plus ui. And your null could have lots of restrictions in it. So it could be that beta j, the jth one, equals some number, beta j0, like 0 or 1 or something. That beta m equals beta m0. Beta m equals 0. Maybe beta j equals 0. And we could have q restrictions. So we could test that q of these things are 0 simultaneously. You just write them all down. In the last case, q is equal to 2 because it was just beta 1 equals beta 2 equals 0. And the null, the alternative then, is at least 1 is non-zero. Okay, so how to test? We'll start in the general case by allowing for heteroscedasticity. What you use is called a heteroscedastic robust F-statistic. And when we look at E-views, I'll show you how to actually do that within the package. Most packages make the assumption that you have homoscedasticity, and we'll come to that in a second. And so you have to press some special buttons to get the heteroscedastic robust F-statistic. But the way you test this is that under the null hypothesis, to test the null, the F-statistic will be distributed f of q and infinity. This is the large sample approximation. So we just act like we have an infinite amount of data. Basically, this is the number of observations. That's infinity. Q is the number of restrictions. So what you do is you have these restrictions, like your null is, say, beta 3 equals beta 4 equals beta 5 equals beta 6 equals 0. 1, 2, 3, 4 restrictions that you want to test. Maybe this is a set of variables about color, and you're doing car sales, and there's 4 different colors, and you want to know, does color matter in general? And so you want to test jointly if these things are 0. The alternative is at least one non-zero. Within the computer packages, there's a way to tell it this is the restrictions that you want to do. And it varies by package. You just have to look it up in the instructions. But there's usually a fairly easy way to do this. So you tell the computer packages which restrictions to apply. And we'll see later they can be richer than these 0 restrictions. These could all equal different things, like beta 3 could equal 4, beta 1 could equal -1, beta 5 could be 0, and so on. And it would still be the same sort of thing. And later we'll see you can actually have like beta 1 plus beta 4 plus beta 5 equals something, or something like that. But this is the simplest case. So you tell the package in some way which restrictions to apply. And again, I'll show you how to do that on another video when we do the computer stuff. And it will give you an F statistic. That's what this is. That statistic has this distribution. So you look up the critical value in the table in the back of the book. And then you're going to reject if the F stat is greater than the critical F of Q infinity, critical. So you look, say, for a 5% level of significance and 2 restrictions. You look in the back, and you say, I want a 5% level, and there'll be a table that has F2 for infinity, and it'll say, if you want a 0.05 level of significance, this is the value of the F that you should use. Then you just take the one that comes from the package and compare it to this. If it's greater, then you reject the null. And I'll do an example of this in a second for the test scores. You can also do it through the p-value approach. The way you do that is the F distribution looks something like this. Here's 0. Looks like this. Remember that the computer package gives you the F stat. So you just find that F statistic. And you can look up in the back of the book what this area will be for that F statistic for Q and infinity degrees of freedom. So it's the F. That's the distribution that this is following. So you look it up in the back of the book. If this, and you'll get an area. If it's less than 0.05, you reject. If it's greater than 0.05, you fail to reject. Essentially what you're doing, say that this is the critical F that you've looked up. That means there's 5% in here. So if you get an F that's less than 5%, you're in the rejection region. If your F is on this side, so that you have greater than 5%, then you're less than the critical value and fail to reject. Again, I think it's easiest to just let the computer do this for you. A lot of times the packages will even give you the critical values if you tell it the significance level. And so with computers, it's fairly easy to do. Okay, a couple more points, then we'll do a quick example. Let me check something here. Okay, good job. I was checking the time. There's something called the overall regression F statistic. So for the model, yi is beta 0 plus beta 1 x1i plus beta k xki, so you have kx's plus ui, that model. The overall regression F statistic is the null that beta 1 equals beta 2 equals ... equals beta k equals 0. It's that none of the x's matter. The alternative is at least one is non-zero. So you're jointly testing, you're asking, do the x's as a group help to explain y? If the answer is no, it's probably not a very good model. As a group, your x's are doing nothing to help you explain y. So a lot of packages spit this out just as part of the normal output. So they'll give you an overall F statistic. One more thing, if there's just one restriction, say we have, again, the same model, and our null is, say, beta 7 equals 0, so that Q equals 1. There's just one restriction. In this case, the F is the same as T squared. And so getting the F for in this case is really simple. You can just look at the T statistic for beta 7 and square it, and you'll get an F. And the test will give you the same answers, and pretty much, not exactly, but most of the time. And so with just one x, F is T squared. With just one x, with just one restriction, F is equal to T squared. All right, let's do an example. The good old test score example. So we had a model, and I can't remember the exact coefficients, but you've got it written down there in your notes. Suppose we want to test that the beta on the student-teacher ratio is equal to the beta on expenditures equals 0. So Q, the number of restrictions, is 2. And the alternative is one of the two is not 0. Okay, from the computer output, you get that F equals 5.43. And that's a heteroscedastic robust F. From the table in the back of the book, you would find that F of 2 infinity, Q infinity, for a 5% level of significance is 3.00. F for a 0.1 degree level of significance would be 4.61. So this is rejected. This is bigger than these. So this is so we reject the null. at both the 5 and the 1% levels of significance. And so this is pretty significant. So we can't reject that those two things as a group are 0. And again, it may be, when we did the t-test, this came out that we failed to reject that it was 0, but that could just be the multicollinearity. This test indicates that as a group, those variables are significant. So let's now look at the homoscedastic only. It only works in that case, F tests. That is, if we're willing to assume that we have homoscedasticity, then there's some very simple and intuitive ways that you can do these F tests. And so in the case where you're pretty sure that you don't have to worry about heteroscedasticity, the problem simplifies quite a bit. So the F test in this case, there's other ways to do this, but this is a nice intuitive way, can be obtained from two regressions. And let's use as an example the null that beta 1 equals beta 2 equals 0 when k equals 3. And the alternative is at least one non-zero. So the first regression is the unrestricted regression I talked about earlier. That's the one where you don't impose these. So with k equals 3, that's yi equals beta 0 plus beta 1 x1i, beta 2 x2i plus beta 3 x3i plus ui, because k is 3. We haven't imposed any 0 restrictions, so that's the unrestricted model. Then the restricted model, we impose the null hypothesis. So yi is beta 0 plus 0 times that plus 0 times that plus beta 3 x3i plus ui. So what you do is you run the unrestricted regression and save the sum of squared residuals from the unrestricted model. So you just tell the computer, run a regression of y on x1, x2, x3, and then just save that number that's on the output. It's almost always there. Second, run the restricted regression and save the sum of squared residuals restricted. Then the F statistic is very easy to calculate. And this always works for any hypothesis if you have homoscedasticity. F is going to be the sum of squared residuals from the restricted model minus the sum of squared residuals from the unrestricted model over the number of restrictions, which is Q. Q is 2 in our case, divided by the sum of squared residuals for the unrestricted model over n minus k plus 1 in parentheses. And just to, so I have it here to point at, recall that the unrestricted model was yi is beta 0 plus beta 1, x1 plus beta 2, x2i, let me put the i's in, plus beta 3, x3i plus ui, and then yi equals beta 0 plus beta 3, x3i plus ui. So this regression is just a regression of y on a constant and x3. You tell the computer to do that, and you write down the sum of squared residuals. If the null hypothesis is actually true, if it's true that, remember our null is beta 1 equals beta 2 equals 0. If that's actually true, then imposing the hypothesis should not have a very big effect on how well the model fits the data. When I regress this, I don't really need these in there to fit the data. This is the only thing that matters. And so when I oppose these restrictions, the sum of squared residuals don't change very much. Imagine starting with the restricted model and saying, okay, if I add these two other variables, x1 and x2, how much does that improve the fit? This is a measure of the fit. This is basically the standard error of the regression model, except we haven't divided by the degrees of freedom. This is the standard error, by the way. If, on the other hand, x1, and so if the null is true, these things should be very close together. You should have hardly any difference in the two sums of squares because the fit won't be any better when you have this. The sum of squared residuals won't go down for the less restricted model because these things aren't helping you explain the data. So this should be close to 0. If that's close to 0, your f should be close to 0. So for a really small f, so we have this f distribution, and out here is the rejection region. That's at the 0.05. Down here for really small f's, we fail to reject the null because these things are close together. Now what happens is, suppose that x1 and x2 do help explain y. Then when I add these variables in, the sum of squared residuals should go down a lot. Or if I start with this model, and I get a sum of squared residuals unrestricted, and then I throw these things out, the sum of squared residuals should go up a lot because I'm not going to be able to explain the data anywhere near as well if I've left out variables that really matter. And so in the case where this should be rejected, there should be a big difference between these two things. The f should be a big number. That should put us out here in the rejection range. Well, how big should f be? Well, that's what that critical value tells you. This is how you always do tests. You find something that's small if the null is true, and then as the null looks less and less true, that thing gets bigger and bigger until you hit a point where you say it looks like it's not true, and I'm going to reject it in favor of the alternative. That's what we have here. We have something that if the null looks true, if these things are close together, then the f is small. As it looks less and less true, as these things move further and further apart in magnitude, the f gets closer and closer. Then at some point we say, oh, okay, that f's so big that we're going to have to reject it because when I added these extra variables in, it made a huge difference in the sum of squared residuals. Now, you can use if you use that, oh, you know, when I wrote that f, it was sum of squared residuals restricted minus sum of squared residuals unrestricted over q divided by sum of squared residuals unrestricted over n minus k plus 1. That's the k for the unrestricted model. In the case I just did, k was 3. Okay, forgot to say that. Now, if you use that r squared is 1 minus the sum of squared residuals over the total sum of squares, you can show that f is equal to r squared unrestricted minus r squared restricted divided by q all over one minus r squared unrestricted, and this is multiplied, not divide, times n minus k, again for the unrestricted model, minus 1, n minus k plus 1 in parentheses. And this is distributed, again, f of q and infinity. And again, this only works for the homoscedastic case. So this makes it really easy to calculate your F statistic. You just run the restricted model, write down r squared, run the unrestricted model, write down r squared. You should know the number of variables in your model, and you should know what n is. Then you can just find your F, compare it to the critical F, and do your test. Great. Now, when n is small, use the homoscedastic only F only if 3 things are true. The heteroscedastic robust one, you need large samples. For the homoscedastic case, you can use the small, it'll work in small samples, but you have to have 3 things true. First, well, n will be small. That's just part of it. I probably didn't need to write that down. Second, it's homoscedastic. So you have to be pretty certain about that assumption. And the third thing is that the UIs are distributed normally with mean 0 and variant sigma squared u. This is the assumption. These 2 assumptions are generally not defensible. But if they are, then the F stat will be distributed F of q and n minus k plus 1. Before it was q infinity because we were just using the large sample approximation as though n was infinity. This is a small sample, so I can't use infinity. I have to use this q, or this degree of freedom. The F depends upon 2 degrees of freedom. Before, the second degree of freedom, there wasn't. It was infinite because we were using the large sample approximation. When n is small, you have to use this particular F distribution. Let's do the test score example. And see what we can see. So going back to our example. So our null is beta STR equals beta expenditures equals 0. We already did this with the heteroscedastic robust test. That's when we got the 5.43. Now we're doing it, so that was under the heteroscedasticity, and we used the heteroscedastic robust F. Now we're assuming homoscedastics. So this is the example with the homoscedasticity assumption. and large N. The alternative is at least 1, not 0. So from the unrestricted model, so you run the unrestricted model, you'll find that r squared unrestricted is 0.4366. That's with all the variables. And you impose these two restrictions. R squared restricted is equal to 0.4149. Remember, the unrestricted model is score is beta 0 plus beta 1 times STR. That's beta STR here. Plus beta 2 expenditures plus beta 3 per pupil expenditures plus beta 3 times percent English learners plus some error. And so that was the unrestricted model, and you get this r squared. It's bigger because it has more variables. Then you throw this out, and run the restricted model, and you get a smaller r squared because you don't have as much ability to explain the data. And the restricted and unrestricted estimated models are in the book. I'm just going to write down the r squareds. So then from there, we can get that f equals, using that formula we just wrote down, the unrestricted r squared minus the restricted r squared, 0.4149, divided by Q2 over 1 minus 0.4366, 1 minus r squared unrestricted, times n minus k plus 1, minus 3 plus 1. That's 420 minus 4. And that turns out to be 8.01. The 1% critical value from the table is f of 2 infinity, because there's two restrictions. We have the large sample assumption, is equal to 4.61. So we would reject that these are jointly 0 at the 1% level of significance. Okay? Now, what we're going to do next is generalize this a little bit and talk about not just 0 restrictions, but any type of restriction at all. And so the next thing is testing a single restriction involving multiple coefficients. So if we had a model like yi is beta 0 plus beta 1 x 1i plus beta k x ki plus ui, we're talking about hypotheses like beta 1 equals beta 2, or a null like beta 1 plus beta 2 equals 1, or that's the null, or beta 1 minus, this is the same as beta 1 minus beta 2 equals 0. Or it could involve three of them. It could be, something like 2 beta 1 minus 3 beta 7 plus 1/2 beta 8 equals 11. Something like that. So some single restriction about the coefficients. And there's two approaches to this depending upon what you're willing to assume. So one way to do this, so there's sort of two approaches. One, and this should work. If the computer package allows, you just tell it the restrictions. So there's a way to input that equation like beta 1 plus beta 2 equals 1 or something like that. You just tell it what the restriction is, e.g. program beta 1 plus beta 2 equals 1 as the restriction. Usually, never, well, it varies by package. I'll show you when we do this for e-gives. So you just tell it what the restriction is, and then it'll either give you the heteroscedastic robust F if you push the right buttons, or it'll give you the homoscedastic only. And that's sort of the standard case. And then you just compare it to the critical value. If Q is 1 here, and we're making a large sample, so 1 infinity. So Q equals 1 in this case, because there's just one restriction in here. And so you just let the computer do all your work. You say, here's the restriction. I push these buttons, give me the heteroscedastic robust F. I push these buttons, give me the homoscedastic F. You look up the critical value in the table. You compare the two. And if these Fs are bigger than the critical, you reject. If they're smaller, you fail to reject. So that's kind of the standard way of doing this. Now, there's another way you can do it, but you're going to need to make the homoscedasticity assumption. But this is fairly intuitive. So let me show you how to do this too. And this is for the homoscedastic case only. Because we're going to use the sum of squared residuals, minus restricted, unrestricted, and so on. Oh, no, I'm sorry. We're not going to do that. But suppose my model is yi is beta 0 plus beta 1 x 1i plus beta 2 x 2i plus ui. What you do, and my null here, is that beta 1 equals beta 2. The alternative is that beta 1 does not equal beta 2. So that's what we want to test. What you do is you impose the restriction in some way. So this is tricky. So let me just show you the example of how to do this. What you're going to do in this case is add and subtract beta 2 x2i. So I'm going to write this as yi equals beta 0 plus beta 1. I'm sorry, I meant x1i. x1i. Literally beta 2 x1i. yi is beta 0 plus beta 1 x1i plus beta 2 x2i. Now add and subtract this. Plus beta 2 x1i minus beta 2 x1i plus ui. So I've just added 0 to the model. So I can write that then as yi is beta 0 plus beta 1 minus beta 2 times x2i plus beta 2 times x1i plus x2i plus ui. And I'm going to say yi is beta 0 plus gamma x2i plus beta 2 wi plus ui, where wi is x1i plus x2i. What I could do is to do a, what I'm interested in, this hypothesis is the same as beta 1 minus beta 2 equals 0. You see that? Beta 1 equals beta 2 is the same as beta 1 minus beta 2 equals 0. Notice that this is beta 1 equals beta 2, beta 1 minus beta 2. So I can do a t-test on gamma to test that restriction. Because gamma will, if gamma is 0, then beta 1 minus beta 2 is 0. If gamma is not 0, then those aren't equal. So testing whether this is 0 is equivalent to testing that beta 1 equals beta 2. So you just go into your spreadsheet and you create a new variable, x1 plus x2, that's what wi is, and you run this regression, yi and a constant, x2 and w, and then you do a t-test on this coefficient, and then the t can give you, if you want to do an f-test, you can. F is t squared, because q is equal to 1 here, and so you can do either kind of a test. What this requires is some cleverness to take your original model and rewrite it in a way that the null ends up as one of the coefficients. And the only way you kind of learn to do that is with practice. But you can always do this, but it's a lot harder. So usually what we do is just let the computer package do all of this for us. Now, you can also have more than one restriction. So take the same model, yi equals beta 0 plus beta 1 x1i, beta 2 x2i, beta 3 x3i plus ui. Our null could be beta 1 minus beta 2 equals 2, and beta 2 plus beta 3 equals 3. The alternative is at least one is not true. That's not equal to that, and that's not equal to that. One of the two is not true. So this is the case when q is greater than 1. Here, q is equal to 2 because there's two restrictions. again, the easiest way to do this is to just plug this into your software, your regression software, and tell it, impose these two restrictions. These are my two restrictions I want to test. So you tell the computer, the software, the restrictions, both of them, and it gives you an F. And then you compare to the critical value for an F of 2 infinity. And you can have even more restrictions. If it just, for just among beta 1, beta 2, and beta 3, you can't have more than 3 restrictions. But you can have up to 3. You can have up to k restrictions. If you included beta 0, you could have k plus 1. But so you could have even more restrictions. And again, the simplest way to do this is just have the software do it. And we could also, another way to test this would be to do what we did last time, which should be to be very clever, add and subtract things until we get these restrictions appearing as coefficients. It turns out there's a way to do that. It's very tricky. I'm not going to have you do that, but we could do that trick again and make it so that somehow this coefficient would be beta 1 minus beta 2 minus 2. So on one of the variables you'd have, this is the same as beta 1 minus beta 2 minus 2 equals 0. And another coefficient would be beta 2 plus beta 3 minus 3. And this one is going to involve adding and subtracting 2's and 3's, and this one will involve adding and subtracting 2's and 1's. And if you manipulate it, you could make that work. I'm not going to do an example of that. So in the heteroscedasticity cases, those are your two options. Have the computer do it for you, which is what we're going to mostly do, or be very clever and rewrite the model in a way that the coefficients, that the things you want to test appear as coefficients. And then you can just estimate that model and test whether that coefficient is 0 or not. In the homoscedastic case, there's another way you can do this. And let me just show you an example. yi is beta 0 plus beta 1 x 1i plus beta 2 x 2i plus beta 3 x 3i plus ui. And our null is what we were just doing. Beta 1 minus beta 2 equals 2. Beta 2 plus beta 3 equals 3. And the alternative is 1 not true. So what you do is we're just going to use that restricted, unrestricted model approach that only works in the homoscedasticity case. So what you do is you just impose the restriction. So yi equals beta 0 plus, this says that beta 1 equals 2 plus beta 2. So plus beta 1 is 2 plus beta 2 x 1i plus beta 2 x 2i, and then sub in for beta 3 here, plus 3 minus beta 2 x 3i plus ui. So this is the same as beta 3 equals 3 minus beta 2. So I've imposed the two restrictions. I can rewrite this as yi minus 2x1i minus 3x3i equals beta 0 plus beta 2 times x1i plus x2i minus x3i plus ui. So let me write this as yi tilde equals beta 0 plus beta 2 wi plus ui. That's the restricted model because I've imposed the restrictions. And this is the unrestricted model. So the way you could test these two restrictions would be first to run the unrestricted model and then save your sum of squared residuals unrestricted or r squared, either one. Remember, we can do the test either way. Then I need to run the restricted model. So what I do is I go in my spreadsheet and I take a column and I make a new variable called y tilde, and it would equal y minus 2x1 minus 3x3. And so you just create a new column with that variable in it, call it y tilde. Create another column called wi, and wi is x1i plus x2i minus x3i. You just make that variable in your spreadsheet. Then you run y tilde on a constant in w, and that's going to give you sum of squared residuals restricted or r squared restricted. And then you just find the f in the usual way. F is going to be sum of squared residuals unrestricted minus sum of squared residuals restricted divided by 2 in this case, because there's 2 restrictions. All of that divided by sum of squared residuals unrestricted over n minus k in the unrestricted model, which is 3 minus 1, or n minus 3 plus 1, if you will. And then that would be your f statistic. The critical, this is an f to infinity, so you just compare this to the critical value, and you can do your test that way. So in the homoscedastic case, even in these multiple linear combination cases, I could have coefficients here too, it wouldn't matter. You can get the f statistic fairly easily by just running the restricted and the unrestricted model. So you just take your unrestricted model, impose all the nulls, put all the things with betas on one side, all the things without betas on the other, form your new variables, run your regression, and you're all set. And so I've given you 3 ways to do these. One is let the computer package do it. Tell it the restrictions, it'll do the rest. The second is be very clever and rewrite the model so that the coefficients of the rewritten model are the hypotheses you want to test. That takes some cleverness. I don't usually do them that way. The third way, if you're willing to assume homoscedasticity, which is dangerous, is to just impose the restrictions, write the model you get after imposing them, and then run the restricted and unrestricted models and use this formula for f that we've learned. Now, there's not that much left. We're running a little long on this video, but the next one would be too short if I stopped. So let me just keep going and finish this off, and you can break up the video as you need. So I guess you can always pause and take a break, so I shouldn't feel like I necessarily have to do this. Confidence intervals, confidence sets for multiple coefficients, for joint hypotheses. Now I'm looking back for the model so I can get the estimates. Where's the one that had 3.87 and 0.29? It's here somewhere. Give me just a second. I thought I had this at hand. I guess I forgot to write it down. It's here, I think. Yeah, this is the one we want. So we estimated this model score predicted as 649.6 minus 0.29 STR plus 3.87 expenditures per pupil minus 0.656 times the percent English learners. And we had some standard errors, 0.032, 1.59, 0.48, and 15.5. And we did a joint test if that and that were simultaneously 0, and the answer was they're not. Now what we want to do is what's a 95% confidence interval look like for a joint hypothesis? And in general, it's an ellipse. Sometimes it's a multi-dimensional ellipse. I'll show you the case for the null that beta STR equals beta expenditures equals 0. That's what we tested. We rejected this earlier. So what does a confidence interval in this case look like? So as I was just saying, it turns out that it's an ellipse. And this is drawn better in the book. So you can certainly look there. This is not 0, 0. This is minus 2 and something. 0, 0 is right there. This is beta 1 hat. That's the STR beta. And this is beta 2 hat. That's the expenditures per pupil variable. And our estimate was this was 3.87. And this one was minus 0.29. So those will be at the center of the ellipse. So what a 95% confidence interval will look like in this case is something like that. This is supposed to be an ellipse. It's sort of tilted that way. And this is supposed to be at the center. I didn't hit that very closely. And so because the 95% confidence interval doesn't contain 0, you would reject the null. If 0, 0 was inside there, you would fail to reject. It's shaped this way because these two things are positively correlated. If they were negatively correlated, the ellipse would be slanted in the other direction. Anyway, I'm not going to do a whole lot with this. I'm going to skip the formula and so on, but I just wanted to show you what the confidence intervals look like for these joint hypotheses. If you had 3 variables, there'd be a third dimension, and it'd look more like a blimp, if you can picture that. And yeah, so that's that. And now the book just throws a topic in, which, again, I'm not sure why it got thrown in at this particular point, but here it is, so let's do it. Omitted variable bias. In multiple regression. Nothing new here. You'll have it if, 1, the omitted variable is correlated with any x in the model. Let me say xi. x1, x2, doesn't matter. It can be correlated with a set of them. Doesn't matter. And it helps to explain the dependent variable, yi. So if that's true, you'll get bias and inconsistency in that particular case. So there's really nothing new here. For instance, we've left outside learning opportunities. Out of the regression. That's probably correlated with family wealth, which is probably, museums and learning material at home. Even having a computer at home, for instance, might depend upon the district's wealth. Affluent districts also have smaller classes, and so you get a correlation between this this consequence of high family income and STR. Since STR is in the model, and since this matters for scores, this probably induces some bias. And the degree of the bias would be higher if the correlation between learning opportunities and class size is higher. So there's nothing really new under the sun there, and I won't say much more than that about it. If your omitted variable is correlated with any of the x's, and it matters for y, you've got a problem. And the problem's bigger as the correlation gets bigger. Okay, model specification. And this is something we'll spend more time on in the next couple of chapters. But let's get started on it here at the end of this chapter. What I mean by that is what variables to include. And if you ever do this stuff for real in practice, figuring out what goes in the model and what doesn't isn't as simple as it might first appear. So how should you make the choice of what variables to include in the model? And this is the last section of the chapter. Well, one, you should choose a core set of variables. So you can usually figure out your core set of variables based upon expert judgment, economic theory, knowledge of how the data was collected, and what that gives you is a base specification. Then over and above that, this is rarely decisive. You usually have a list of candidate or potential variables that you're not quite sure of. Should I include this in the model or not? Does this really matter? Is this an important variable to include in my model? I'm just not so sure about that. Then you've got a bunch of variables you're just absolutely positive are going to make a huge difference. The first thing you want to do is just check the robustness. So what you do is you just take these candidate variables. So you run your baseline model. You look at your coefficients and your R-squareds and all those things. Then you throw in these variables, either all of them or some of them, and you do a bunch of different regressions, and you keep looking at your results. And if the betas on your baseline variables just don't change very much, if your R-squared doesn't change very much, if the model's robust, well, the R-squared might change, but if the coefficients in particular don't change much and their standard errors don't change very much, then your model's robust. to these other candidate variables, and it really doesn't matter whether you include them or not. And so often you get lucky and your model just doesn't depend upon the particular specification in terms of these other candidate variables. When there is a lot of difference, then what's going on is you probably have an omitted variable problem, because including some variables makes a big difference in your results. And then exactly how you should proceed is a little more tricky, and we'll take that up again in Chapter 9. And so we'll come back to this specification issue in Chapter 9. But for now, the idea is you do this base set of variables, things you're sure are in the model, you put in your other candidate variables, and you try a bunch of specifications, and you see how much variation there is among them. Now, the last point on this specification is interpreting R squared and R bar squared in practice when you're actually doing this stuff. What do they mean? So a lot of people see a high R squared or a low R squared, and they come to some wrong conclusions. So a high R squared or R bar squared near 1 is high. What that implies is that the regressors, the x's, are good at predicting y. Remember a long time ago we said just because something's good at predicting y doesn't even mean it's causal, and we'll come back to that in a second. But it's easy, particularly for people first starting out, to read too much into these statistics, to make too much into it, read too much into R squared, into high or low R squared and R bar squared. And so here's 4 points. Then we're done. 4 points about R squared and R bar squared. The first is that an increase, suppose you add a variable to the model, and you want to know whether that was a good idea or not. An increase in R squared or R bar squared does not mean the variable is statistically significant. You have to do the test to find that out. So just because it goes up doesn't mean anything in terms of how important that variable is in terms of its statistical significance. So you have to do the t-test, or if you're doing a joint hypothesis, an f-test. You have to do the t-test in that case. And this is the prediction point I just made. A high R squared or R bar squared does not mean the regressors, the x's, are the true cause of y. It's raining right now. That's a big surprise for Oregon, I know, but it is really. And if I were to regress the weather on the number of umbrellas I see people carrying, what I'd find is a statistically significant relationship between when it's raining, when it's bad, crappy weather, and seeing lots of umbrellas. But umbrellas don't cause rain. So just because I can regress the amount of rainfall on the amount of umbrellas, and I get a significant T and maybe even a high R squared, that doesn't tell me anything at all about whether the X is the true cause of Y. The book's example is if you regress test scores on parking lot size for teachers, you tend to get a pretty high R squared, but there's no causation there. What you're picking up is probably class size, because you need more parking lot space for more teachers. So you're picking up an expenditure or something else. But the parking lots aren't causing the low scores. And so R squareds and T's don't really tell you about necessarily about causality. Third, a high R squared or R bar squared does not mean you're free of omitted variable bias. You could have a high R squared and still have things that are left out of your model. It could be even higher. And fourth, a high R squared or R bar squared does not mean you have the most appropriate set of x's, of regressors. And more importantly is the converse as well. The converse is true. A low R squared does not necessarily mean you have a bad model or the wrong thing. You could just have a model where there's a lot of randomness, where the UI just has a huge variance, and that's going to give you a low R squared. That doesn't mean that the variables you have in your model aren't significant, aren't important, and aren't the true cause of YI. It just means you have a lot of noise, a high degree of noise in the relationship. It's something that's hard to predict in generally, so there's a lot of UI variation, but you still might have things that are important and can help you to figure out, on average, where it's going to go. And so high R squares doesn't mean you have a great model. Low R squared don't mean you have a bad model. Sometimes in micro, they'll have models with R squared as low as like 0.1 or 0.05, and yet they'll have a very nice model. Okay, well, that ends Chapter 7, and I will see you again soon.